Hi everybody, welcome to this talk. My name is François Serre. I hope you're doing absolutely fine and staying safe during this pandemic. Today I'm going to talk about neural network verification tools, why you need them, and what you can expect from them. I will talk about a tool that we have developed, GPU Poly, and the techniques we employed to make it work on state-of-the-art neural networks with the highest possible speed and with zero compromise on the accuracy. This work has been done in collaboration with Christoph Müller, Gagandeep Singh, Markus Püschel, and Martin Vetchev. Okay, let's get a bit of context first. Obviously, I cannot poll the audience at this moment, but I guess that everybody has already heard about adversarial attacks. The idea is very simple. Let's say that you have a network that classifies pictures of animals. This network is well trained and has excellent accuracy in every picture you have tried. Now we take a specific picture of an animal, let's say a dog. On the picture it looks like a dog, you feed it to the network and the network says it's a dog, and it says it with good confidence, so no problem here. An attack would consist in taking this picture and change a tiny little bit the values of the pixels in such a way that you, as a human, would never see any difference with the original picture. But when you run inference with your network on this new picture, the network outputs that it's another animal, let's say a cat. There's been plethora of work on how to design such attacks. They exist in all domains where you can find classifiers: computer vision, speech recognition, finance, healthcare, aviation. There has been research on how to target a given specific output and on how to find robust attacks. When I say robust here, I mean robust in the sense that the network would reliably be fooled on a given example, even with some perturbations. This is needed if you want to have attacks that can be implemented in real life. Here is an example of a robust attack on a visual classifier. They have 3D printed a turtle, or at least something that for a human looks like a turtle, but that is reliably classified as a rifle by the network they're using. The second example here is an adversarial attack done on speech recognition. The authors propose several audio files. When you listen to them, especially here the first and the third, you are not capable as a human to notice a difference. But a speech recognition system will hear here two different sentences. The work that I'm presenting here is a tool that can be used to test if a network is vulnerable to such attacks. More formally, a verifier would work the following way. It would take a neural network, a network that has already been trained, and so we would input both the structure and the training weights. However, a network is not robust in the absolute. It may be robust around a given input vector, an image for instance. This vector would be the second parameter to the verifier. The last parameter would be the perturbation size that you would allow. It's a parameter that specifies how far away from the input vector the guarantee should hold. If we choose it to be 0, then the tool will only tell whether the network correctly classifies the input. And the higher this parameter is, the stronger the guarantee will be, but it also means that it's more likely to fail the verification. Then, ideally, the verifier would run its computation and answer whether or not the network is robust around the test input. Unfortunately, giving such an answer is hard, NP hard, and if we want a tool that would scale on networks as large as those presented during this conference, we need to compromise somewhere. And the point on which we compromise is on the answer of the tool. We accept that the tool may not be able to certify all cases. Therefore, it becomes possible to get a possibly non-robust answer, even if the network is actually robust. Now the answer robust is still a strong answer. It means that in the area that you have specified, you will never find any counterexample. Of course, the challenge consists in minimizing the number of robust cases that the tool fails to certify. It would be easy to have a tool that would always answer possibly non-robust, but that would not be very informative. I guess you can already feel here that there's going to be some sort of trade-off between speed and accuracy. And this trade-off translates into the model that you choose to approximate the problem. To explain in what consists the choice of a model, I will now take the example of a small classifier. This classifier takes as input a picture made of two black and white pixels, so it might not be the biggest kind of picture you have seen in your life, but somehow the classifier is able to classify this input into two output categories, cats and dogs. As you can see, this classifier consists of an affine layer in light green, followed by a ReLU activation layer. At the end, the network has two output neurons, each corresponding to one of the two categories. As every layer in this network has two neurons, we can represent them in a 2D plot. For instance, here, if we associate the intensity of the first pixel to the x-axis and the intensity of the second pixel to the y-axis, then we can represent an input picture as a point on this graph. For instance, this point here. Now the inference takes place. After the first affine layer, our point has moved a little bit. After that, we have the ReLU layer. As the two coordinates are positive, then the point stays at the same place. Now we have to classify the point, and it's assigned to the category for which it has the highest component. In other words, if it's below this dashed line, then it's classified as a dog. Otherwise, it's classified as a cat. Here it's a dog. Now we would like to know if our great classifier is immune to adversarial attack on this picture. To do that, instead of considering only one point, we consider a whole neighborhood of our picture. Here the square that you see is the set of the pictures that are at less than a given uniform distance from the original one. The goal is here to check if, after inference, all these points are classified as well as dogs. So the first layer rotates a bit the square, translates it a bit and squeezes it a bit in both directions. Then comes the ReLU layer. You see here that the points that are below the x-axis are trimmed, such that the points remaining are in the upper right quarter. As our shape lies below the dashed line, all the points are classified as dogs and the certification holds. Here you see that on this particular example, we managed to solve the problem directly by computing the exact shape of the output area. However, as said before, doing it this way is NP hard, meaning that scalability may become an issue. An idea that is used in many verifiers consists in considering a simpler model that will approximate the actual area. Of course, this model should always represent a superset of the actual area to make sure that we never get false positives. Many of such models exist. In this presentation, we will focus on two of them, the bounding box and the polyhedron. These are the two models that we use in GPU Poly, the tool that we propose. The first one, the bounding box, is the simplest one. The idea is to take an upper and a lower bound for each neuron. If we take our previous example, the area we use to define our problem fits nicely within such a bounding box. It's the box represented with blue borders. Now to propagate or to relax our model through the network, we just have to apply some sort of inference on the bounds. The only thing that one needs to be careful about is to switch the upper and lower bound when multiplying with a negative constant. This sort of spatial inference is called forward interval analysis. After the first layer, we end up with a bound like this. Now you see that the blue box over-approximates the actual area. There are some points that are within the blue box, but that do not belong to the actual area, the gray area. And this is a situation we would like to avoid, because as you can see, when we continue the relaxation with the ReLU, some of them fall into another category, and so with this model we cannot conclude anymore. For this reason, we say that this model is only approximate on affine layers. Now this being said, if you look at the ReLU layer, it doesn't add any additional over-approximated area. And for this reason, we say that the forward interval analysis handles ReLU layers exactly. I will now talk about the second sort of analysis, namely Deep Poly. This is the main model that we use in GPU Poly. I will not explain fully here how it works, but just give some insights. So as its name suggests, Deep Poly uses polyhedra. A polyhedron is a bit similar to the box that we just saw, except that each face has more freedom. It doesn't need to be perpendicular to one of the axes, and it can freely rotate. And this has a big advantage. Now a fine layer can be represented exactly. You can see here that there is no space between the green area and the gray one. However, Deep Poly has some limitations. To prevent combinatorial explosion, the number of faces for each polyhedron is limited to twice the number of neurons. This is the reason why, in the ReLU layer, it over-approximates the area in order to not create a new face. Now, on average, Deep Poly is usually a lot more accurate than the bounding box. But this higher accuracy comes at the price of a much higher computing cost. And that's expected. The number of coefficients that are needed to define a polyhedron is higher than the number of coefficients to define a bounding box. Therefore, by intuition, the relaxation steps will be more complicated than for the forward interval analysis, which, as we saw, has a cost of around 2 inferences. To give some figures, forward interval analysis runs in O of ln square, where L is the number of layers in the network and n the average number of neurons per layer, while Deep Poly runs in O of L square and cube. To give some perspective, here are two plots that compare the accuracy and the speed of both deep poly and forward interval analysis. Both were tested on the same network, a classifier that works on the MNIST dataset and that was trained for robustness using cron IBP. For different perturbation sizes, so this is the x-axis on both plots, 100 input vectors were tested. The plot on the left shows how many could be certified out of these 100. The plot on the right shows the runtime per input vector. Note that on the right plot the y-axis is in log scale. And as you can see, deep poly is way more accurate. For a perturbation size of 0.25, it manages to certify 75% of the candidates, while the forward interval analysis couldn't certify any. However, you can see that interval analysis is way faster. It takes a constant time of 3 milliseconds per input, while deep poly takes 7.5 seconds. This represents the trade-off I mentioned earlier. One is fast and inaccurate, the other is slow and accurate. In GPU poly, we combine the two approaches to get the exact same accuracy as deep poly, but with a much higher speed. To explain how GPU poly works, we need to look into the way deep poly handles the ReLU layers. If you remember, I mentioned earlier that deep poly was approximate on ReLU, but there was an asterisk. There are actually cases where deep poly is exact. Let's consider the example of a ReLU on a neuron X. There are three cases. Either the input polyhedron is completely on the right side of the plane x equals 0, meaning that for all its points x is positive. A second possibility is that it's completely on the left side. Lastly, a third possibility, the plane x equals 0 intersects the polyhedron. In the first case, deep poly doesn't modify the polyhedron at all, and this is an exact transformation, as it is exactly how a ReLU would operate. In the second case, deep poly flattens the polyhedron in the plane x equals 0. Again, this transformation is exact. The only case where the transformation is inexact is the third one. At some point in the algorithm, deep poly needs to figure out for each neuron of each ReLU layer which of these three cases is relevant. And to do that, it computes the extrema on the x-axis of the polyhedron. This operation is called back substitution, and it's extremely expensive, as it involves matrix-matrix multiplications for all the layers that precede. The idea of GPU poly is to use interval analysis to try to skip this costly operation. Therefore, instead of doing the back substitution directly, we first use an interval analysis to get a bounding box. This is the box that appears in blue. Note that the faces of this box have no reason to correspond to the extrema of the polyhedron. But this box may be already sufficient to conclude that we are in one of the first two cases. This happens if the plane x equals 0 doesn't intersect the box. In this case, we don't need to perform any additional computation, as deep poly is already exact in this case. However, if the plane x equals 0 intersects the bounding box, we need to use the Rellwegen, the back substitution. And this back substitution may lead to either of the three cases. Last point, if a back substitution occurred, then we can use its results to refine the bounding box. This way, the interval analysis will be more precise for subsequent layers, and the next ReLU layer will be less likely to trigger a back substitution. The effect of the optimization we discussed can be seen by taking back the two plots we have already seen. By construction, GPU poly is as accurate as deep poly, however, we can see that its speed has significantly improved. For small perturbations, no back substitution ever has to take place, and GPU poly is as fast as forward interval analysis. Then its runtime increases exponentially as more and more back substitutions have to be performed. In this example, the runtime of GPU poly always stays orders of magnitude smaller than deep poly. In theory, the worst possible runtime of GPU poly is when all back substitutions need to be performed, and in this case, the runtime is equal to the runtime of deep poly. As mentioned before, the algorithms used in GPU poly heavily relies on matrix-matrix multiplications. In addition, when dealing with convolutional networks, several conv2D and conv2D transpose operations need to be done. The best platform to implement this kind of embarrassingly parallel numerical operations is a GPU, and therefore this is the platform on which we have developed GPU poly. I will now explain some of the challenges we faced. There exist libraries for our building blocks, namely cuBLAS and cuDNN. Unfortunately, we couldn't use them as they were not compatible with one of the features of GPU poly, floating point soundness. Floating point arithmetic has finite precision, 1 and 2 to the minus 24 are perfectly representable as single precision floating point numbers. But their sum is not. This means that when you add them together, and if you have not touched the default rounding mode of your system, you will get exactly 1 as a result. If this happens when you are computing an upper limit, then your bound will be inexact. This means that we need to be able to choose the kind of rounding we want, depending on the kind of limit we are computing. In addition to this, additions are not associative. If you consider the expression shown here, depending on the order of evaluation, you can either get 2 to minus 24 or 0. And this is an issue if you want to capture in your bounds the rounding errors that could be made during inference. In this case, you have to take the next representable number for each term of your sum, in the direction that depends on the bound that you are currently computing. This is the reason why we implemented linear algebra libraries ourselves. For the matrix-matrix multiplication, we used the Cutlass template library to deal with tiling. In addition, creating our own convolution transpose allowed us to handle some sparsity cases, giving us some marginal gains. To give an idea of the impact of being floating point sound on performance, it multiplies the runtime by a factor between 2 to 5, and it uses twice more memory. The reason is that in case you don't know in advance if the operation you are computing will be used for an upper or lower bound, then you have to store both values, the value that you obtain when you round up and the one you obtain when you round down. Now we can compare quickly GPU Poly with a state-of-the-art verifier, Cron IBP. Here we have taken a rather large network that counts 34 layers. And you can see that GPU Poly is capable of analyzing images on this network with a median runtime of 35 milliseconds while having a better accuracy. The runtime heavily depends on the training that was used. Here the network was trained against adversarial attack with a method called DFAI. But if we look at another network that has roughly half the size but was trained with another method, projected gradient descent, then we can see that the runtime performance of GPU Poly is way worse, 10,000 times worse. Note, however, that Cron IBP doesn't manage to certify any image with this network. So as a conclusion, you can find in this slide all the features of GPU Poly I talked about, along with a link to download its source code compatible with both Windows and Linux. I hope that you have learned something during this presentation and that you have survived my accent. I wish you a very pleasant day.